And what that's about is example 4 on page 192. And I'll read it to you. We mentioned it the other day, but we didn't do anything with it because we're out of time. The radius of a sphere was measured and found to be 21 centimeters with a possible error in measurement of at most 0.05 centimeters. There's several different words there that are interesting to me. And one is a possible error. There may or may not be an error of at most. So they don't know whether it's an error or not, but they know how bad it can be. That doesn't make too much sense to me. Anyway, what is a maximum error in using this value of the radius? And the point I made the other day is the answer we get in this problem is not necessarily the maximum error because there's no inequalities if you look in this problem. An inequality of maximum error would be greater than or equal to something. Okay, so now the question is how you do the problem. And in this case, because it's a sphere and because it's a volume, then the author writes the usual sort of stuff. V equals 4/3 pi r cubed, because one way or another we're told or we know that that's the volume of a sphere. Okay. Now, because of the way things are done here, we're not changing the volume in time. We're talking about a possible error, and so the r is changing. It is a function, and v is changing depending on what the amount of error would be. But basically, v is a function of r in this particular case. Okay, not both of them a function of t. So if we make a function, basically the volume is a function of the radius. Okay, and I just do that because I like to use functional notation. And he says if the error in the measured value, which we're told, the error, he says, well, we don't know. The radius was measured to be 21 centimeters with a possible error of 0.05. Okay. So possible error. Now, what does that mean? That means the real amount is 21 plus or minus 0.05. We don't know, but it's in that range somewhere. That's what we're basically saying. So what he does in the problem is he says the error in the measured value is denoted by dr or delta r. This is, I told you the other day, this is where people write all this stuff because they're still stuck with delta and d's in this problem, in these kind of problems, and there's no reason to be. But this is basically taking notation from 200 years ago and still trying to think it's relevant, which is not. Anyway, so all I would be doing is maybe calling this H or something, just using a different letter that isn't connected with D things or delta things. I'm using H, they're using something else. Doesn't matter what we use, but what is the differential? So if we have a function f, and if we're doing something, I'll do something at A, we say the value at something a little bit off is approximately the value at the place plus what we call the differential, which is this number here. And this is the dy, if you like, when that is the dx. And so this is the amount of working out what the slope does involving the function. So we're going to, or the derivative, it is a slope, but we need to differentiate here if we're going to approximate something by this kind of formula, okay? And what are we saying that the volume is and stuff? So let me show you what he's going to do. okay, he's going to say dV is 4/3 pi. Now, yesterday, I guess it was, I said when somebody says take a differential, what do they mean you do? They mean for you to take a derivative and then stick a dx on the end of it. Okay? Well, in this case, it's not a dx, it's a dr. So we take a derivative. Derivative would be 4 pi, and the derivative of r cubed would be 3r squared. That would be the derivative of the volume formula as a function of r. And then we stick dr in at the end of it. Okay? So in this particular case, the 3's would cancel, and you come up with 4 pi r squared dr as dv. Okay? Now, the dv is the dy. What you'll notice here is this thing, the derivative of f at a, that's the derivative of v at r. And next to it is a x or a dx. Now next to it's a dr. Now in this problem, dr is measured at 0.05. So if we start filling in things we know, we would put 0.05 here. 4 pi is just 4 pi. What's the radius involved here? The only radius we've been given was r was 21. So you put 21 squared here, which everybody knows, I guess, is 441. Maybe. You have to figure that out. Okay. Maybe that's right, maybe it's not. I don't know. I just put it down. I'm a professor, so everybody believes me. You don't use your calculator here necessarily. I would just change this to 5/100 maybe, and whatever. Okay? Now, when he works out this stuff, he's going to get dV. What does dV mean? That's the differential. That's the amount different. Okay? In this case, remember, I wrote it this way. I'm going to write it with V's now. The V at something plus H, in this case, it would be 21, is approximately what happens at 21, okay, plus the differential dV. So this is the amount that's going to measure the error between what you get and what you are supposed to get. I'll put it differently. This is what you got, and this is what you're supposed to get, because this involves the error. Okay? So this is the volume with the error in it. Now, by the way, you don't know what the error is, remember. But the volume, a little different than the one you measure. So this is the volume you get when you measure by the formula. This is the thing we're trying to approximate. We use a so-called differential to measure the difference of the two. This is the error. So he wants to know, what's this number? Well, we just figured it out. Now, I didn't write it out. When he writes it out, he comes up with 277. Is what he comes up with. Now, whatever you come up with, is this an exact number? Why not? Because of pi. Okay, so if you were really doing this problem for real, I mean, where you're in a business or a company or something where you're really interested in the answer here, okay, because it might make a difference as to which machines you use or whether you buy new machines or whatever, okay, because there's quality control and things like that. You'd want to know how much tolerance do we have to error in the product we're producing. And once you know what the tolerance is, you know how accurate you have to be, and you'd know what degree of accuracy you'd have to write down for pi, so that when you work it out, you'll get something within the degree of error that you're allowed to have. Okay? In other words, I don't, in the mathematics world, we leave the real numbers as real numbers until we need to approximate. We don't in a thing change all the numbers as we go. Oh, this is 3 point, by the way, in 1890, there were several different states that declared state law, including Kansas, that pi is exactly 3. Became a state law for a while. Because the legislators, they didn't know what to do when they're building roads and stuff and talking about how whether bridges should have trucks go over them and stuff. They, horses, just call it 3. It's easy. State law. Okay? So that'd be nice. It's just the question comes down to, is that within the degree of accuracy needed when you build a bridge? For example. Okay, anyway, what I'm trying to say here, this is an approximate number based on an approximation here. What we ought to start out with a problem and say we want to be able to do this with a certain amount of accuracy, Steve. But basically this problem isn't about real life, it's just about trying to get you to understand this is where the error is going to, you add something here to the measured value to try to say about how much the error might be in the volume. Okay, the word maximum shouldn't be used here because I don't know, we're saying within plus or minus here, and so this is within a certain thing here, but I don't know which is maximum and which is minimum. We just found one number and we didn't compare it to anything else. So anyway, just the example is mainly to figure out what dV is. And the second thing, what he really wants to tell you about is something called relative error. Now, whatever this number is going to be about this number. About. Okay. So he says in the book here, although the possible error may appear to be rather large. What is this 277? 277 is 277 cubic centimeters, I guess, because it's volume. How big is 277 cubic centimeters? Well, it sounds big. But is it big compared to the original volume when you have a radius of 21? See, one person is a big deal in 2 people, that's 50%. It's a smaller deal in 1 million people. Okay, so what people do here is they might want to know the maximum error or about what the error is, but they also want to know how big a deal is it for the problem in mind. Okay, so if we go back to the math, not this one little problem, we go back to the math about this and do this dV thing I did over there again. The relative error is what we found divided by the original volume. Okay, and so what we do sometimes is do it in general. Namely, the dV I wrote here is 4 pi r squared dr. What if I would put that here as 4 pi r squared dr, okay, and divide by v, which is 4/3 pi r cubed. When you do that, you learn that first of all, the pi's cancel. That's good because that's the place where we didn't know how big it was. The pi's cancel, the 4's cancel, the 3 goes upstairs, and 2 of the r's cancel. So what do we get out of this? The relative error in the volume is about 3 times the relative error in the radius. And that is what people use more than the number 277. So you're saying if I make a little error in the radius, it's going to the magnitude is about 3 times the air in the volume. 3 times, okay? So relative air is a measure of how bad the air in a piece propagates into the air of the whole thing. And if you can tolerate that amount, you go with the thing, okay? So you make a small relative error, it's going to be a 3 times, but still a relatively small relative volume, you see? So all people are doing with this stuff is trying to get an idea of whether or not it's satisfactory. But I thought we ought to talk about that a little bit once you sort of absorb this whole idea of differentials. All these symbols don't mean much. Basically, as I said, I just call this H and I avoid these things, but it's everywhere. Once you've had calculus background in all the fields where people use calculus, they all use this bad notation. So I want you to know about the bad notation because that's what you're going to run into. And if you start talking to people about functions, they won't understand you. And they may be your professors. I'm not being mean, I'm just saying it's all about functions, but historically it was about variables, and some people are still stuck in that because that's the way they learned it. Okay? So I just wanted to tell you that that's chapter 2.9. So you could have a relative error question on a test. And whatever it is, you have a formula. Like I can give you a square or a cube. What's a cube? The volume of a cube is just this. You can figure the relative error in that. How do you do it? You take the derivative of, because now this is a function of s, right? Now you take the derivative and divide. The dv would now be something ds, and you divide by the original formula and you get another thing. That's for a cube. I'm just making that up. I can give you a formula and ask you what the relative error is, and you divide the differential, quote, by the original, whatever. Okay? Okay, chapter 3 is, now, I know we're doing stuff before we have a test, but it's only because I'm being nice to you to give you a test a week ahead. Okay, I could have said the test is tomorrow, and we could not do chapter 3, but since, and I was asked by people not to do chapter 3 yet. The point is, I don't have to do chapter 3 yet, but then we'll be doing chapter 5 and 6 in 1 week at the end. And we won't be together because after Thanksgiving, we will be remote. You don't want to do 2 chapters in 3 days. I mean, I can do that, but you guys don't. So we have to have some kind of pace. We've been going too slow already, but I'm hoping you're understanding something. That's the game. Okay. So what's in section 3.1? It's titled Maximum and Minimum Values. Now, one of the reasons to do chapter 3 is to learn how to graph. So if we assume we don't know anything about graphs, we can't use a graph to tell us much. But I'm going to back that off a little bit. We can't use a specific graph to tell us much. But you all know what graphs look like, not what a particular one looks like, but graphs are some kind of curve things. Everybody knows that, I think, whether or not you know what a particular one looks like. The one I just drew here would be continuous, it appears. Also, it appears to be differentiable everywhere. Why? It would appear to me any place on that curve I would want to put a little piece of paper, as long as the paper wasn't very long, in this case would be a line, but as long as it wasn't very long, it would rest. It wouldn't fall off. Okay? So it appears the way I drew it is it's differentiable and it's continuous and all that kind of good stuff. All right? And that's the kind of assumptions we're going to make about these things that we're going to deal with. Now, also, I think it's obvious where it's increasing and where it's decreasing. That's where it's going up and where it's going down, y values. Okay? And when it's curved down like this, now, the definition, which the author does not make, the definition is when you have something like this and you take any 2 points on the curve and draw the straight line between them, if the line lies below the graph, okay, then the curve in that area is called concave down or just concave. If, when you look at a curve and you connect it with 2 points and the line is always above the curve, this is called convex or concave up. Now, when you draw a curve, the one I drew, I have concave up and I have concave down pieces, all right? And so there are intervals in which I have concavity up and concavity down, but I have to have one or the other. Now, what about a flat line, straight line? Is that concave up or down? Well, it's neither, so in a way it's both. And it depends on whether we are going to allow equality. In other words, is this line less than or equal in height than this, or strictly less than? Okay. That brings up the idea of strictly convex or strictly concave. Because if I take a horizontal line and draw put 2 points on it and draw the line is not below, but it's less than or equal. You understand? And it's not above, but it's greater than or equal. So we have to decide sometimes that, like, for example, to me, increasing means as you go to the right, you go up. What does non-decreasing mean? When you go to the right, you either go up or you stay the same. You just don't go down. Okay? So I like to say something's increasing or is decreasing. I'm going to write down some words and letters and stuff in a minute. Or I like to say non-increasing or non-decreasing. Other people like to say increasing, which is either staying the same or going up, and if they want it to always go up, they say strictly increasing. So if you look at different books, or what you had in high school, or what you do find in the library, or what you find online, you got to be careful, because what some people mean for increasing, other people mean strictly increasing. Okay? Now for me, I like increasing, which would mean strictly if you like, and non-decreasing. So to me, a horizontal line is non-increasing and non-decreasing at the same time. Okay. Anyway, what that has to do with is saying if x, let's say s, if s is less than t, then f of s is less than f of t. That says if you pick two numbers and you pick s and you pick t and t is to the right of s, what about the heights? The height on the right will be higher than the height on the left. This is what I mean by increasing. And there's something, again, that we should always do that I forgot. I didn't forget, but I want to make a point of it. What's left off here? For every s and t somewhere. In other words, what you need to be talking about here, if you look at this graph, sometimes it's going up and sometimes it's going down. So you have to know where it is you're talking about. In other words, this particular picture is not always increasing and it's not always decreasing. But on certain subintervals, it's increasing. It satisfies this. So where would it be increasing? To me, from about here over to somewhere around there, it's increasing. Okay? From about here up to somewhere up in there, it's increasing. Somewhere like that. So this would be increasing in two intervals. That's what I meant by somewhere. So we ought to be saying is take any 2 points in that area. Now, a little problem with what I wrote here. I said it's increasing here and it's increasing here. So if I take something here, does that mean it's less than something here? See, if I take S here in this piece and T over in this piece, is this one higher than that one? Not necessarily, right? Because they're two different pieces and it's a different place, and right? So I gotta take somewhere and say maybe in some interval. In other words, in this interval, is it going up? And in that interval, is it going up? Because if I just take where it's going up, that's two intervals, and you can't say this thing. You can't use this definition. All right. Now, in some notes I gave you before, intervals were called connected. You may remember. We also have closed and bounded intervals that are called compact. And I introduced those things, said don't worry about it. We'll talk about it later. Well, we're going to start talking about it. Okay? Anyway, an interval is a connected set. If it's a closed interval, it's called a compact set. Okay? And we'll be bringing that up in a few minutes more. Anyway, everybody understand what would non-decreasing do? How would I change this definition here to non-decreasing? It means things are either staying the same or going up. All that means is I need to put an equal possibility over here. See? S is less than T, so S is here and T is here on the line. And the height is either equal or greater on this part. That's called non-decreasing. So non-decreasing puts an equal sign here, whereas strictly increasing or increasing does not have an equal sign, it has a less than. Okay? Now, there's another word we have to worry about in books, and that's the word monotone. Now, monotone, the word means one sound, technically. You all know if anybody goes to churches or synagogues or mosques or whatever, and you sing in any of these places, there's always somebody who sings off tune in the audience. The only problem with those people is they always sing loud. And so I've heard people declared in a singing situation that that guy's a monotone, meaning he only's got one sound. You know, whatever the notes are, the guy says, that's all that comes out. You all know what I'm joking now a little bit, but you kind of understand what I'm saying. Okay. Now, if someone speaks in a monotone voice, what are they kind of doing? They're not doing anything like that. Okay. I'm sorry. How many of you jumped at home? Anyway, monotone is a certain way of speaking. Okay. All right. So, what does that mean mathematically? When things are either increasing or decreasing, or either non-increasing or so on, we call those monotone. In other words, it takes care of both situations. When I say something's monotone, it means it's non-increasing, or maybe it's non-decreasing. I'm just trying to tell you it's either kind of going up or it's kind of going down. And I said kind of because different books describe it different ways. For some people, it's only with the less than or equal. It's only the non-increasing and non-decreasing they call monotone. Okay. Other books do it differently. You have to look at the book to see what's in the book. It is I'm not even sure, but I'm not certain that the word monotone is in the index here. I'm not going to take time to look it up now. but it may not even be in the index in this book. Okay, but you can have books that have whole chapters on monotone functions, for example. And that has to do with functions that are going up or functions that are going down in some way. Anyway, so I'm trying to clear out some cobweb words here that you'll find, and you'll wonder, what does that mean? Well, it may differ in each book. Absolute maximum here, no. Relative maximum, we covered this yesterday. Local maximum, absolute maximum. Okay? Absolute minimum in this particular case, again, it happens at the end point. Now, what we're going to do in everything we do with stuff is always deal with the endpoints separately. So whatever we do, we're going to test things at the endpoints. The calculus is going to come in testing things in between the endpoints. So I have a formula. We'll take derivatives and things in between the endpoints, and the endpoint questions will always reserve and do it anyway. Okay? Even though I can see this is a low point, I would be testing it. Now, is this lower than that? I don't know. If I think from standing here it is, but you'd have to test such a thing. Okay? Now, what are we testing? Okay, well, in section 3.1, you learn, after you go through those things, there are two theorems on page 206 and 207. Okay, one's called the extreme value theorem. Now, you and I have already had this in our notes. Let me read it to you. If f is continuous on a closed interval, now, that's a compact set, we said, then f attains its absolute maximum value and its absolute minimum value someplace in the interval. Now, what I tried to detail to you in those notes once, if I have a continuous function on a closed interval, okay, now it may not be in the first quadrant here at all, but just a picture for you guys at home. What do you know about the image, the values of the function above here? They will be an interval. If the domain is an interval, that's a closed and bounded set, and a continuous function, the range will be an interval. A closed and bounded interval. That's what I gave you in the notes some weeks ago. Now, if the range is a closed and bounded interval, then it has a highest place and it has a lowest place. Okay? So that's what the extreme value theorem says, that someplace, whatever this graph looks like, okay, whatever it looks like, and I didn't quite make it quite small enough here, whatever it looks like, someplace in here, there will be a place where it hits the bottom, and someplace will be a place, in this case, where it hits the top. Because the range is going to be an interval. That's what I showed you. Now the book, you notice, if you read page 206, it says, the extreme value theorem is illustrated. Note that a function can attain an extreme value more than once. Now, although the extreme value theorem is intuitively very plausible, it is difficult to prove, and we omit the proof. Now, what you do to prove it is talk about compactness. So I introduced the concept to you that you use to prove the theorem, but we didn't do anything with it, and we're not going to do anything with it. But I'm kind of going one slight step further than the author. The author says he's just going to omit stuff. I'm telling you, if you learn about compact sets, that's how you prove it. Okay? And we could prove it, but I don't. Some of you haven't been able to read anything I've written so far, so I don't know why reading another page of a long page and a half of proof is going to help you in it at the moment. In any event, that's available to you. If anybody wants to see the proof, I can show you. But I don't see any reason to do it in the class at the moment. Basically, intervals become intervals, either a continuous function. So what you do if you have a picture like this over here, I would say, what's the range of this? Okay, and I don't know where this particular picture is. Suppose the y-axis is over here. What's the range? It would be anything from about here up to about here. Okay, because the whole function is defined on a big interval, and the top point is it's hit here, and the low point is hit somewhere. Anyway, The extreme value theorem says you always have a maximum and minimum for a continuous function defined on a closed and bounded set. All right. Second one, Fermat's theorem, according to the author. Not always called that. Fermat's theorem is something you already believe in, I think. It says if a function has a local maximum or minimum at a point, now points are always interior to the domain in the book. If you have a local maximum or local minimum, and if the derivative exists, then the derivative is zero. Now, if I look at this graph that I drew, there are three places where the derivative is zero. Okay? And those occur at high points and low points on the graph. Such points will be called critical points for us. Okay? A critical point will be for us an interior point of the domain where the function derivative either doesn't exist or is zero. Okay? So what you do when you have a formula is you look for places not where the function's zero. The function zero is where you cross the axis. When y equals zero, you're crossing the axis. In high school, sometimes you try to figure out where were the zeros of the function. We still want to know that. This particular graph I drew up here earlier doesn't have any zeros, meaning there's no places where it goes through the origin. Is that a question?
Yes, I have a question.
Yeah.
About the theorem. What if the maximum or minimum is at the endpoints?
If it's a closed and bounded set, that's included.
Or is the function differentiable at the endpoints?
Don't know. I mean, for the function, we're assuming it's continuous only, not differentiable. So it's continuous on a closed interval means that the left-hand limit is what you expect it to be, and the right-hand limit over here is what you expect it to be. No talk for that extreme value theorem about differentiability at all. Okay? Sometimes you have to worry about that. In that particular theorem, we don't. Later, we will. Okay, so that is a, the problem is, earlier on, we learned that I define derivatives and continuity stuff at accumulation points, and the author only talks about them at interior points. And so some of the conclusions I would draw differ slightly at endpoints from what the author would say. And that's why I stopped a second, is because it is a problem that authors have with how do you handle endpoints. So the question you're asking is a good one because it's a problem. Okay, it does come up. So anyway, I hope for this one I answered your question, but it will come up again in other situations. So in any event, what the theorem on page 207 says is that where you know you have a maximum and you know the derivative exists, it must be zero. Okay? Now, you could have a graph with something like this. This would be a place where the derivative does not exist. It still has a maximum there, but it's certainly not a place where you have a tangent line. So we have to include the possibility of the derivative not existing. And so we throw together derivatives not existing together with derivatives being zero to call them critical points. Now, not every critical point, you have to be careful. It is not an if and only if condition. And the function thing we use, and we're running out of time in class today, but this particular one, this graph, if we knew how to graph it, and again, we don't know yet how, okay? But the graph is going to turn out to be something like this. And at this point, the graph is flat. It's flat at one point only. If you've ever climbed mountains and need to spend the night on the mountain, you look for a place like this. You look for a flat place on the mountain. That's where you stay. Okay, hopefully it's more than one point. It's difficult to sleep on one point. But the thing you look for is this kind of a place. Because it's a flat place among no flat places, basically. No. So anyway, I don't know if any of you have experienced that kind of thing or not, but the point is, it's possible here for the derivative to be zero without being a maximum or a minimum. Notice on the left it goes down, on the right it goes up. This is neither a max or a min, but the derivative is zero. So it's a critical point, but not a maximum or minimum. On the other hand, what's the theorem say? If it's a maximum or minimum, then the derivative is zero. It's an if-then sentence. The converse is false. Okay? This is one reason to do logic. Okay? So the theorem only goes one way, as it turns out. And those two things bring up critical numbers. And the author then, on page 209, talks about what he calls the closed interval method. It's 21 after, I see. And he's beginning to talk about how we're going to draw graphs. Now, what we need to do is bring in positive and negative derivatives and positive and negative second derivatives before we can really do that. That's further in the chapter. The very first part of the chapter is just trying to get you interested in finding critical points. So let me stop the recording.